In section 3.7, we talk about modeling using variation. So variation formulas show how one quantity changes in relation to other quantities. And quantities can vary directly, inversely, or jointly. And we're going to look at each one of these separately. So the first one is direct variation. If a situation is described by an equation in the form y equals kx, where k is a non-zero constant, we say that y varies directly as x, or y is directly proportional to x. We say that that number k is called the constant of variation or the constant of proportionality. Now, can you see that the direct variation equation y equals kx is just a special case of the linear function y equals mx plus b? If I were to let m be k and b be 0, then y equals mx plus b now turns into y equals kx. So how do I solve variation problems? First, I want to write an equation that models the given English statement. Then we want to substitute the given pair of values into the equation in step 1 and solve for k, the constant of variation. Then we're going to substitute the value of k into the equation in step 1 and then use this equation from step 3 to answer the problem's question. So y varies directly as x, y is 45 when x is 5, and then we want to find y when x is 13. So we know direct variation is set up as y equals k times x. The first thing we need to do is we need to find that constant of variation, k. So we know that y is 45 when x is 5. And so now we can easily solve for k by dividing both sides by 5. And so we end up getting that k is 9. So let's go ahead and plug this back into the original formula. So y equals 9x. We just replaced the k. We want to figure out what is y when x is 13. So we're just going to do 9 times 13, and we get that y is 117. A direct variation situation can involve variables to higher powers. So this was just a singular x, but we can have x raised to the second power, third power, fourth power, and so on. So y varies directly as the nth power of x if there exists some non-zero constant k such that y equals k times x to the n. We also say that y is directly proportional to the nth power of x. So it's okay to have x raised to a power other than 1. Now let's talk about inverse variation. When two quantities vary inversely, one quantity increases as the other decreases, and vice versa. So if a situation is described by an equation in the form y equals k over x, where k is a non-zero constant, we say that y varies inversely as x, or y is inversely proportional to x. That number k is called the constant of variation again. So notice that the inverse variation equation is just a rational function. We use the same procedure to solve inverse variations as we did with the direct variation problems. So first you want to find your k, and then you find what the actual question is asking. So if y varies inversely as x, that means we have y equals k over x. We need to find k first. So when y is 9, x is 3. And so to get k by itself, we're going to multiply both sides by that denominator of 3. And we end up getting that k is equal to 27. And we want to plug it back into the original. So y equals 27 over x. We want to know what y is when x is 6. So that's 27 over 6, which we're going to get a decimal point, and we get y is 4.5. In combined variation, we're just combining direct and inverse variation at the same time. So A varies directly as B and inversely as the square of C. If A is 7, then B is 9 and C is 6. We want to find A when B is 4 and C is 8. So the hardest part is setting up this equation. So A varies directly, so A equals KB, and inversely as the square of C. So that inversely means we're going to write a fraction bar, and the square of C is C squared. The first thing we need to do is find K. So when A is 7, B is 9, and C is 6. So we end up getting 7 equals 9K over 36. And we need to solve for K. So we're going to multiply both sides by 36. We get 252 equals 9K, and then we want to divide both sides by 9. And so we end up getting 28 for K. And then remember, we want to plug it back into the original. So we get A equals 28 times B all over C squared. Now we want to know what A is when B is 4 and C is 8. Well, 28 times 4 is going to give me 112 divided by 8 squared, which is 64. And again, we're going to get a decimal, and we get that A is 1.75. And the last type of variation is joint variation, and this is a variation in which a variable varies directly as the product of two or more other variables. So it's all multiplication, but we have more than one multiplication occurring. So kinetic energy varies jointly as the mass and the square of the velocity. A mass of 8 grams and a velocity of 3 centimeters per second has a kinetic energy of 36 ergs. Find the kinetic energy for a mass of 4 grams and a velocity of 6 centimeters per second. So let's write down our formula first. Our energy, which I'm just going to label as E, varies jointly, don't forget your K, as the mass, so M, and the square of the velocity, so V squared. And jointly is just more than one multiplication. We need to find K first. So we know when we have a mass of 8 and a velocity of 3, the kinetic energy is 36. So we have 36 equals K times 8 times 3 squared. Well, that's 36 equals K times 8 times 9. And that gives me 72K. And we just want to divide both sides by 72. And so we get 0.5 for K. Then we want to go back and plug it in. So E equals 0.5 mv squared. We want to know what the energy is when we have a mass of 4 grams and a velocity of 6. So E equals 0.5 times 4, and then times 6 squared. Well, that's 0.5 times 4 times 36. And that's going to give me 72. And this is in ergs.